Astrostat. This is a truly a workshop course. We literally work here. And over the years, this is how many years now? 20 some years, 25?
1997.
Since 1997, we started this course when David Van Dyke, who's now in England, he started here when he was a faculty here. And I think David and Anita and also Vinay. Where's Vinay? Vinay is there. Vinay is there. There are the few, and also Alana unfortunately passed away now more than 12 years ago, or something like that. And so this group has always been kind of working together, and astronomers, astrophysicists bring their problems. There are lots of problems because they deal with the whole universe. How many problems there. And we, the statistician, kind of I used to be. David was here. He was in charge when he left. I took over. Said, kind of my job is helping to organize the students to work on these problems. So there's really no lectures. We're basically you'll be seeing lots of presentations. And for any of you, if you take this for credit, the requirement is just you present at least once. And it does not really mean that you need to be a very kind of a developed project. In fact, Taka will be a good example. That Taka was a student here. And Taka, what year you were here? Now it's almost like
I was sitting there in the first class of that course in 2013.
2013, okay, it's more than 10 years ago. And I think Taka's project, you must present over what, 20 times or something? It's over a long time because
yes,
they come to present and we say, well, it's like a research group, right? We discuss and get lots of comment, they go back and we keep doing that. And so over the time, he did a lot. And also I think all these people listed here on this certainly is all belong to this, what we call the CHASC. Over the time, I think this group has, David, how many members ever we have had? 40, 50?
At least, yeah.
A lot, right? We have lots of students graduated. Most of them go to various departments are doing like astrostat. So lots of astrostat group around the world that have connection with this group, and we just keep doing this. And typical sizes like this, it's going to be a very casual, small ones, and then the course is over the year, so it meet every other week. But usually we don't necessarily every other week. On average, every other week. Like I think the next week we have one. It sometimes depends on people's schedule. We're all busy. Sometimes we skip like 2 or 3 weeks. Then we have couple weeks intensively work on it. Okay. So welcome to any of you that if you ever there's some problem we come up with, then you say, oh yeah, I want to work on that problem. You're more than welcome to give a try. And we have what we still call the Hilbert 23 problems. Actually more than 23 problems. They keep adding this list. I don't know how many problems listed there. It must be 30 problems. And Anita, you're going to talk about that. Not today, I know. On the 12th. So no, not 12th.
No,
later.
When Vinay is back, so I don't.
When is back.
Yeah.
Okay.
We'll circulate.
Yeah. So this particular paper, Talk is going to present. Talk has been, and we all together, we have been working on this for what, 6 years? Something like that.
Yes,
right?
almost 5 years.
Yeah.
More than 5 years. More than.
We got invited because the center, the group is quite well known. And so we were invited by one of the editors from which journal?
AAS.
Okay. Well, you have to say what AAS means.
AAS, the American Astronomical Society, like the ASA in statistics, they contacted us. It's not just one specific journal.
So then they invite us, particularly invite Talk, and to say, well, why don't you guys writing an article about, there are lots of misuses of statistics in, out there, and they're good uses, they're misuses. So this is more about, some guidelines, some, high level principles, and particularly with the application in astrophysics. So with that, and Talk, you take over. Okay.
Oh, thank you so much for nice introduction. I remember I was sitting in the science center, that classroom in 2013, as I said, but my motivation was not to learn astronomy or some astrostatistics because my motivation was having free lunch, catering there.
That's a good one.
But at the end of the class, the first class, shall Kelly said that it's all about the data. You don't need astronomy. And actually, Vinay and Aneta helped me to learn astronomy. They brought me some topics, and I'm still working on that. It's my great pleasure to be the first speaker of the class of that academic year. I forgot the catalog number of the class. Astro 303, something like that. 313?
310. 310.
310. Yeah, I was there. So, okay. Today I'm going to talk about 6 maxims of statistical acumen for astronomical data analysis. This is joint work with Yang, everyone in the room or in this group, almost. Yang, Vinny, Casey, Xiaoli, Aneta, and Dave. Okay, so this is a background. The statistical editor of American Astronomical Society, this is equivalent to the ASA, American Statistical Association in statistics. The statistical editor contacted Jogesh Babu, Dave Doug, and me on January 21st, 2019, more than 5 years ago.
Tuck,
Yep.
it's not full screening yet.
I think it's on.
It's on one side problem?
Yeah.
Oh, you're saying it's on my side problem, okay. Okay, give me 1 second. Yeah, you're probably right. It's on my side problem. Let me see if I can fix that.
Use the whole
Yep.
screen, yeah. Oh,
Well, that doesn't work. Let me see if I can,
oh, there you go.
it's on my side. Yeah, sorry about that. You're right, thanks. It's on my side, bro.
Maybe it's being
Okay,
transferred.
yeah.
Okay. So that was the motivation. They wanted to set up some guidelines for principal data analysis in all of the AAS publications. I believe they contacted me not because I'm experienced as statistician as the others, like Jewish Babu, David Van Dyke, not comparable, but because I'm in the same institution with the statistical editor of the AAS. Okay, so that was the motivation, and Jogesh asked David and me to lead the guidelines. So we invited all of the people, most of the people in the CHASC, our CHASC collaboration, and we started talking about what should you write? Why do we need these guidelines? What are the unique features of astronomical data analysis? So we focused on some unusual features of astronomical data, because that will motivate us to write down something unique in astronomical data analysis. So we listed some of them here. So for those in 310, the first year PhD student possibly. So these are the unique or unusual features of astronomy we have been dealing with. So data are not obtained from design experiments, definitely. So this is not a control experiment. Okay, you're the control treatment group or Mars, Venus, you're in the placebo group. We can't do that. So definitely some conditions are not controlled. I mean, for example, there will be some supernova, but we cannot repeat that phenomenon over and over again under the same condition. That's some unique feature in astronomical data. Calibration of this term is crucial in observation process. It needs to account for some correct some uncertainties and bias unique to some instruments. Sparsity is inevitable even with big data. That means even if telescopes surveys the entire sky, probably some of them are not interesting. I mean, not all astronomers are not interested in the entire data set, but maybe interested in some portion of some patches of the sky or some dimmer objects to find some new to find some new discovery or new classes of astronomical objects. So even if we have big data, our interest may be some narrow part of the big data. Astronomical objects evolve on the different time scales. It means that when we survey the entire sky, astronomical objects may be in the different stages of their life cycle. Some of them is dying, some of them is just created, but they evolve on a definitely different time scale from ours, much larger than ours. So from our perspective, probably they move quite slowly. I mean, they change it quite slowly, but I mean, each object may be on a different time scale. Lastly, I mean, not lastly, but one of the unusual feature in astronomy data is that measurement error uncertainties are heteroscedastic. It's not homoscedastic in a simple linear regression or linear regression in general. And one more unique feature in astronomy data is that those measurement error variances are typically assumed to be known. I mean, they are given in one column just next to your measurement. So that's one thing unique. So considering all of these unusual features, probably it's not straightforward about how to apply some standard statistical methods to analyze these data set. For example, even linear regression may not be directly applicable to astronomical data because astronomical data has some unusual feature, heteroscedastic measurement error, and some selection bias, selection effect, and et cetera, et cetera. And we need to take more care when we use this standard statistical method. I think that was our motivation, and so we came up with 6 maxims. I mean, we try to mimic the famous quote, like all models are wrong, but some are useful. So we, in the beginning, for more than 5 years, we tried to cover the entire life cycle of data. I mean, from the production, preprocessing, analysis, interpretation, et cetera, et cetera. But at the end of the day, we focus more on modeling aspects. So let me just repeat one by one. So the first maxim was all data have stories, but some are mistold. And the idea is if we have more stories behind the data, probably we can improve our modeling. Second, all assumptions are meant to be helpful, but some can be harmful. This is to emphasize that direct application of standard statistical tools may be harmful because some of the underlying assumption may not be consistent to the unusual features of astronomical data. The third one is all prior distributions are informative, even those that are uniform. This is try to emphasize the current kind of convention of using uniform priors too much in the astronomy literature. I will tell you what might be a problem or problems. And the first one is all models are subject to interpretation, but some are less contrived. We emphasize some community effort to investigate some specific models, specific model interpretation over time, because many people, I mean, because in order to reach to the consensus, it needs some time. I mean, many researchers to demonstrate pros and cons of the model and the interpretation, what might be a limitation, et cetera, et cetera. And then we may have some time-tested models and interpretations. We want to emphasize that. The fifth one is about testing procedures. All statistical tests have a threshold, but some are missing, or some are missing. I realized that in some articles that I encountered, they didn't even set up any threshold. They just report the significance level of the evidence in the data. That's it. They just leave the interpretation to the users without any testing threshold, but just wanting to tell people that statistical test needs threshold, presets the threshold before any hypothesis testing. And the last maxim, it was a recent word thanks to Yang here. So we could have the 6 maxim covering some data replication. That's pretty common topic in data analysis in both frequencies and Bayesian perspectives. So the 6 maxim is about all model checks consider variations of the data. I mean, replication, like in a hypothetical scenario in frequencies analysis, or some posterior predictive replication in Bayesian setting. But we believe that some variants are more relevant than the others, depending on what we condition on to generate those data sets. And these are the 6 maxims that we covered in the recent manuscript. And I'm not sure whether I'm eligible for the lead author, but fortunately, I was the junior researcher among all others at that time. Probably that's the reason, and that's probably the reason I'm speaking in front of you. I mean, through the Zoom. Okay, let's do the first maxim. I enter this maxim into ChatGPT and see what image ChatGPT produces. So all data have stories, but some are mythical. Probably this person is storyteller. He's telling some stories behind the data. Some may be mistold. I don't know how to emphasize that aspect, but this is an image that ChatGPT produced. Probably, if you're using some paid version, probably your image may be better, but this is the free version, the product of the free version. Okay, as I mentioned, one thing we want to emphasize is that if we know more and more about the story behind the data, then we can improve the modeling and correct some possible model misspecification. And we gave 4 examples on the 4 categories about sampling mechanism, selection effect, pre-processing, calibration. Let me tell you each of them. By the way, this is just overview of our manuscript, so some details may be missing. So if you have any questions, please feel free to jump in. So sampling mechanism. Clearly, astronomical data are not a random sample. By saying random sample, we mean that every object in the population has some known positive probability of being in a sample. It doesn't need to be uniform, equally likely to be sampled, I mean, depending on the sampling method. But at least the probability of being in a sample should be known, and it should be positive. Definitely, this is not the case in astronomical data because it is likely that bright objects or closer objects are more likely to be in a sample, and some of them are too dimmer, not being in consideration at all. And non-uniform coverage is related to that as well. As I said, some brighter objects have more probability of being in a sample, or closer object, the same thing. And if we don't account for the story behind the data, I mean, meaning that if we are not considering these data are not a random sample from the population, possibly it will lead to a biased inference in astronomical data analysis that was also but detailed in a linear regression setting by one of the group members, CHASC group member, Brandon Kelly. He is 1 generation above me, so I couldn't have a chance to meet him. But when I started in 2013, he was already outside of this field. He went to industry for some practical reasons. Okay, that's it. So we wanted to emphasize that stories behind the data are important. And in terms of sampling mechanism, we gave an example of Hubble constant estimation because in the early stage of the Hubble constant estimation, the Hubble constant estimates are overestimated. Probably because this is because systematically high peculiar velocities in nearby objects that we cover at that time. But as we collect more and more data, and as we learn more stories behind the data, as we improve data, we could improve the models. And I mean, that's kind of iterative procedure to improve our model. So as time goes, definitely Hubble constant estimates goes down and in the boundary below 100 kilometer per second per megaparsec, even though we still have some tension between early and late universe Hubble constant estimates. But just wanted to emphasize that it was some iterative procedure of learning more stories behind the data, correcting systematics, and improving the model. And we may need that procedure to reach out the better inference.
So, Chuck, do you know if this is settled or this still continuously?
This is still ongoing. Probably they are diverging still. Of course, there are some estimates in the middle, but I believe they are diverging, even getting larger and larger standard deviations between them.
I can comment This
Yeah,
is-
go ahead.
Yeah, so for people who don't know astronomy, this is the basic, most important constant for the cosmology, Hubble constant. And there are still different methods depending which instruments you're using. So you can measure the constant at the high distance, far away, and also using the lower distance measurements. And there is a big difference between the two. I mean, big difference is what TAC highlight there. And the question is why and what's different about these methods, and whether there is a way to merge and get the one estimate, which is good.
Can you help to define what the constant is? Is it really constant? It's a
Well,
physical
it's the
constant.
measure of the expansion of the universe. So the unit is megaparsec per the velocity. So per second of megaparsec. Yeah, it's a velocity. How fast?
But why can't that itself change over time?
It may, yeah,
Wait.
it depends on the cosmology. Then
Yeah.
the question depends on the model of the cosmology.
If I understand right, it's accelerating.
Yeah,
Yeah.
so it's like a function of t, right?
Yeah, yeah. So it's function of time. So we don't, you know.
So it won't settle because it is self, but calling the constant probably is misnorm, is it?
Yeah, I mean, it's called constant because it's this one.
Variable, we
It's
should
not
call
a
it.
variable constant this time.
Yeah.
Oh, yeah, we have astronomers.
Real ones.
And also your
Yeah, I know, astronomers. Okay.
Yeah, we are trying.
Go ahead,
Oh, go ahead. Sorry for interruption.
go ahead.
Oh yeah. So we are trying to measure the expansion speed, expansion rate of the universe. We know that the universe is expanding in an accelerated rate, but the Hubble constant is about the expansion rate at this time, the current time, some time point. So it seems to be assumed to be a constant at the current time, but definitely it is accelerating later. Any questions or other stories behind this? Okay, that's one thing. And selection effects. This is also important and unique feature, unusual feature in astronomy. So astronomical data are typically obtained intentionally or purposefully from some research proposals. For example, some researchers want to monitor some portion of the sky, and data are being generated depending on his or her purpose. And then once these data are being archived, and probably some people may use them as if they were randomly or uniformly selected from the population of interest, possibly unaware of the danger of selection effect, because the original data definitely have some selection effect, but once it is open to everyone, some people may use it as if they are random sample of things. So this is we also introduce some examples where the selection effects matter. So when we match or merge multiple catalog data set, I mean measured by different instruments, definitely we need to account for the selection effect, how they are obtained, which portion, and what is the probability or sensitivity or instrument, etc., etc. And the issue of using these data, publicly available data as training set is that, okay, what's the meaning of training set? We want to learn about something from microcosm of the population. But then if this training data is biased in some way, purposefully or intentionally, definitely we need to account for that. And this group, CHASC group, also had that issue in astronomical classification. So Max, I feel his name. So Max was trying to reduce that selection effect by matching the important aspects, features of the training set and test set. I think this is about some causal inference kind of matching, and important re-weighting as well to reduce the impact of the bias of selection effect between training set and test set. and the pre-processing, clearly astronomical data we receive, we download it, go through many procedures from the raw image data. And this is an example. This figure is about an example. This figure is an example of pre-processing in Rubin Observatory, LSST. One thing we need to keep in mind that in each stage, some people may make an inference, some statistical inference, treating the previous estimate as a data. So in one step, they probably make a statistic inference on the given data, and then they generate the estimates, and these estimates are passed to the next step, and people in that next step treat these estimates as data, make another inference, pass the estimate to the next, etc., etc. So it is important to account for those pre-processing steps as much as possible, because at some point, some systematics were introduced in the intermediate step, and we don't know that if we just treat them as constant, as a data. So we also propose some examples. Possibly from this group or neighbors, our friends. So in cross identification problem, when you merge different catalogs, accounting for their different pre-processing steps and making some consistent data set. Okay, calibration. This was fun to know that calibration in astronomy may be different from calibration in statistical literature. Calibration in astronomy is about process of characterizing uncertainties and bias corrections induced by different telescope or instruments. But if we Google calibration in statistical literature, you will realize that okay, the calibration problem is motivated by chemistry, but it's more likely inverse regression problem among different instruments. Of course, if the mapping is linear, that definitely inverse regression is also linear, so it may be consistent to uncertainty and bias correction of the signal, because that should be linear function of the signal. But definitely they are written in a different context, so people may be confused. If you try to learn about calibration in astronomy from the statistical literature, there will be some misnomer, or not misnomer, but different notation and terminology. Definitely details of calibration should be incorporated into the model, because it may affect the quality of the resulting spectra or resulting X-ray data. And this group has a long history of doing research in calibration in X-ray data from 2011, Lieto, probably even before we have some references. And recent work, Yang and others, Shelley and Marshall from MIT, and we consider in the same group possibly. So even though I mentioned 4 cases, what we want to emphasize in this maxim is that knowing the story of data behind the data is so important to correct or improve the modeling and correcting some possible model misspecification. If we know more, we should incorporate more into our model. Do you have any questions before we move on to second maxim? If you don't, or any good question, which can be naive question from first year student, because I have no idea. If I think about myself, probably I had 100 questions because I wasn't in astronomy side at all. So please feel free to jump in if you have questions. The second maxim, all assumptions are meant to be helpful, but some can be harmful. I just entered this maxim into ChatGPT, and this is a result of the free version of ChatGPT. Probably it catches. Go ahead.
Well, I just said that it's hard to believe that ChatGPT comes up with this nice images stuff.
Yeah.
Now it's very common.
It looks like based on this naive image, I can see what ChatGPT tried to capture. Seems like if you're building something based on helpful assumption, it's strong, but if you're building something based on harmful thing, then it may not be stable. good image, I believe.
Yeah.
Okay, what we want to emphasize under this maxim is that naive or direct application of well-known standard statistical tools may not be reasonable because as we studied, astronomical data have its own unusual features. So popular statistical model were developed for specific purpose, probably mostly outside of astronomy. So standard statistical tools may not reflect those unusual features automatically. So it's our job to modify the standard statistical tools to account for those unusual features. So even linear regression needs corrections because astronomical data may not be normally distributed, measurement error variance, or variances are not homoscedastic, and also measurement error variance are typically assumed to be known, etc., etc. So there are many. Go ahead. Anyone? Fabrizia?
I can just noise that.
Oh, okay. So there are many unique, unusual features that prevent us from direct application of standard statistical tools, just because standard tools have some underlying assumption that are not consistent to astronomical features. So checking assumptions of popular standard models is important when we apply these tools to astronomical data, and we have some statistical procedures like residual analysis or some autocorrelation, some normality tests or some etc. So there were many astronomical examples where astronomers themselves improve the standard statistical tool or tailor standard statistical tools for astronomical purposes, including our Casey here in 2017. One thing we wanted to emphasize is beyond the standard model checking tools, because in our research we found that standard model checking tools couldn't improve our models. So here is one example. We wanted to estimate one specific the model parameter in our model for gravitational lens light curves. We want to find the time delay for this specific quasar Q0957 plus 561. I realize that most quasars in astronomy have this telephone number. Sometimes it's negative, so it looks like telephone number. Anyway, so that's your unique identification number. So here is one thing we found that it is important to check our domain science knowledge to improve our statistical model. So on the left-hand side, we set up a specific model and we wanted to find the posterior distribution of time delay parameter. And it has two modes, one near 400 days and the other group of saddle modes near 1,100 days. And we realized that after we seeing this result, we just got curious. What might be the time delay for this quasar in the literature, and realized that most literature were talking about time delay near 400 days. And then we have this question: what these modes indicate? What these modes tell us? We spent some time to figure out what these different modes are, and we realized that okay, probably we need to go back to the data the literature about this data and see whether we correctly modeling all the aspects behind the data. And we realized that we forgot to add or incorporate this micro-lensing effect, some common phenomena in strong lensing data set. So we added some additional extra modeling aspects reflecting on this story behind the data that we forgot in the first analysis. And after we incorporate that story behind the data into the model, the modes near 1100 days just disappear. It turns out that these are spurious caused by our model misspecification. Of course, standard model checking tools will not tell us, oh, you forgot this phenomenon. You forgot to model this. It is all about based on checking on some previous studies and checking the stories behind the data again, and improving our model reflecting that. So that was one thing we want to emphasize. It's not only for standard model checking tools, but we sometimes need some astronomical, the domain science knowledge to improve our analysis.
Hug,
Yeah.
before we go on, do I remember correctly that this multimodality motivated you to study RAM, right?
Yeah. So
This mistold story had a positive benefit.
yes.
You end up develop the RAM because dealing with multimodality.
Yeah, that's
Is
right.
Is that right? Okay.
That's right. Some assumption was harmful but beneficial at the same time because because this motivated us to develop some MCMC tool to explore multimodal distribution. And this is ongoing essentially. Right now, even I'm improving that method in 2018. It was fun because when we first encountered this left-hand side figure, we thought that it might be a statistical problem. Maybe our MCMC wasn't exploring the multimodal distributions well. So we set the direction to correct this by improving some statistical methodology, like developing something new. But it turns out that the problem was from astronomical side, so so some scientific phenomena that we forgot to model. But so it took a year to move from the left-hand side to the right-hand side. But during that 1 year, we could develop something new methodology. That was another story.
Let me just add before those, I guess some of you are at least familiar with Michael Monte Carlo, right? This is and what Tuck at the time, what he called a RAM. What is a RAM? Repulsive.
Repelling, attracting metropolis.
Yeah, okay. But because what he suggested was very interesting. The typical metropolis Hastings algorithm, as you know, that if you are at a lower density place, if a high density place, you go high proportionally to the ratio, right? So you will over the time it will correct the frequency. But the problem with the metropolis Hastings, as many of you, if you have done it, you know, it tends to be gets trapped somewhere you cannot move out. So what Tuck suggested was instead of moving up using that standard ratio, he actually reversed the ratio. You do the reciprocal. So you do the kind of anti move when instead of going to higher place, you have a high probably go to lower place. At least in the beginning, the idea is to make the thing mixing better. But then you try to correct it for it. So there's this repelling sort of a first push away, then you go back. So there's these two steps. And essentially, is that actually corresponding to using like in a simulated annealing, you're using like a negative temperature. So you do the reverse one. There are benefit of doing so. And I think that's being further developed. What happened to the paper you worked with a physicist?
It is still under review. We submitted.
Where did you guys submit to?
In March, but then it's
no, where?
So Journal of Machine Learning Research, because
See,
the first author likes that journal.
Yeah. Okay, so that was an interesting idea, by trying to deal with this multiple problem.
Changing your stationary distribution if you are.
Well, because there are the correction steps, so eventually the station distribution is still correct. There's a way to correct it. Right? You basically push out, then you come back. You do it.
So it's not a proposable distribution, or is it like re-changing the ratio you're using?
You change the ratio. Oh, I let talk to.
Just in the metropolis ratio, just taking inverse of the ratio makes exploring the inverse word, like flipping word. So the mode in the original word becomes the base in the inverse word. So in this case, by flipping flipping back the ratio in the following proposal step, preserve the correct stationary distribution. We could prove that. Is it the question whether we preserve?
Yeah, that's
stationary?
right.
Yeah, definitely. We came up with an idea to. I mean, definitely exploring inverse words wouldn't preserve the correct stationary distribution, but by coming up with the following step in a unique way, we could preserve the correct stationary distribution. So trying to go down, trying to going valley first, and trying to
Then
go
go up.
higher probability density again, basically repeating procedure. And recently, one of my students developed Hamiltonian version of that idea, exploring the multimodal distribution. So it is still ongoing, but definitely this topic is originated from this left-hand side, the figure on the left-hand side.
Ironically, it's so interesting. All right, that's it's an interesting side story.
So to the
Move on.
first year people in Stat 310. So thanks to this harmful model mystification case, thanks to my ignorance of some interesting story behind the data, I could develop the model, I could get the degree. So sometimes harmful stories are helpful. Okay, so another popular topic in astronomy is about chi-square minimization. This is very widely used method even in classical astronomical literature. And even now, some people are using chi-square minimization often. And when we use chi-square minimization on Poisson counts data, basically the underlying assumption is that the Gaussian approximation to Poisson counts are accurate. But that approximation may not hold well, or the approximation accuracy is low. In several cases, for example, if the estimated variance based on the Gaussian approximation can be quite different from the variation of the observed counts, Poisson counts, definitely the approximation is not valid in that case, and the underlying Poisson assumption may not hold even before. So definitely the following Gaussian approximation is invalid, and also based on the binning of the signals, the counts in some bins may be too small. So in that case, Gaussian approximation to Poisson count is very inaccurate. So these are common issues in chi-square minimization method for Poisson counts. Basically, chi-square minimization is the maximum likelihood estimation, but we are assuming that the data are Gaussian. So we are trying to find the most likely values of parameters by minimizing this chi-square, sum of chi-squares of the Poisson count. Okay, but in order to avoid those issues of the invalidity of the Gaussian approximation is to model the count data directly, which is not common in astronomy, but definitely Brandon Kelly in our group did that in the past, trying to disseminate the idea in the early 2010. And it also has advantage. Definitely, we don't. Of course, the binning itself may be an issue before modeling the Poisson counts. But if we have the appropriate binning, then definitely directly modeling Poisson count has some advantage, avoiding this unreasonable approximation assumption behind the chi-square minimization. And also, it has some advantage of facilitating some model comparison, because model comparison based on the chi-square minimization model has some one more layer which may not hold accurately. So definitely it has some advantage, and we wanted to emphasize that building a model based on directly on the Poisson count is better, because and there are another reason as well. And we also talked about central limit theorems, because central limit theorem is about asymptotics, and asymptotics results are based on some regularity condition and large data size. And we warn some cases where regularity condition does do not hold or some data size are too small to use the central limit theorem from asymptotic result. For example, optimality result of maximal likelihood estimator and asymptotic distribution of likelihood ratio test statistic. These are based on some regularity condition, and Yang here Yang's recent study and this group study recently handled this issue of asymptotics. What happens if asymptotic doesn't hold? Suggesting some alternatives. Chi-squared, the asymptotic distribution of likelihood ratio test statistic will only hold when the two model has some nested relationship. One model being compared should be a special case of the other. And the simpler model shouldn't lie in the boundary of the parameter space. That's also a requirement, and that's even earlier study in this group. I think Protesov, I mean, Aneta Vinay probably know him or not, her. And also, yeah.
Rostislav Kotasov was a student here at that time. He was one of the first students at CHASC working on the problem.
And I believe this paper was talking about posterior p-value in testing procedure.
Yeah, well, it was describing the issues in the standard modeling of the data with the line in X-rays, and people used the assumption that of the likelihood ratio test, which was incorrect for this case. And
the null distribution is on the boundary of the parameter space. So the standard likelihood ratio test assumptions fail, and so you can resample under the null to get the sampling distribution and p-values.
Yeah.
Yeah. Oh, so another issue for asymptotic is whether we have large data sets, because if we have more data set, we need more. If we have more parameters, we need more data set. Of course, some regularization may helpful when the data size is smaller than the number of parameters. Young's recent work suggests some alternative in goodness of fit test when the data size is not large, where asymptotic result doesn't come in. So I think this is the entire idea is about conditioning in the when we reproduce the hypothetical data under the null in goodness of fit test. And okay, we are in the middle. Maxim 3, all prior distributions are informative, even those that are uniform. I think ChatGPT produced this outcome. Probably he or she tries to generate some informative distribution under uniform distribution in the square, on the square. Something uniform was actually informative. So this maxim was motivated by my observation that this is really difficult to find astronomy literature that conducts Bayesian analysis without uniform priors. Most papers are using uniform priors. I mean, sometimes uniform on a logarithmic scale, on a log scale. Too many, I believe. So we thought about why astronomers like Bayesian analysis in general, and why people like uniform priors in most published articles in astronomy. So probably one reason, I mean, possible reason, was that they might think that interpretation of Bayesian inference is more straightforward than frequentist counterpart. For example, like confidence interval versus credible interval, the interpretation might be more straightforward, conditioning on the data. But then, is it all? I mean, definitely Bayesian inference interpretation has also some subtlety in the interpretation, because when people use log of quantity as uniform, do they consider that on the original scale is the informative prior. I mean, in their interpretation of the credible interval, definitely credible interval, the interpretation of credible interval must reflect these informative choices because their result depends on their choice of priors. In many settings, based on my observation, possibly wrong, astronomers just assume some uniform distribution, typically bounded uniform distribution, possibly on the original scale or log scale. And then after getting the posterior distribution, they make an inference. But I haven't seen some inference where they give some warning that their interpretation is based on this log uniform prior, possibly informative, and we check the sensitivity of this prior choice, and this is robust. Our result and scientific findings are robust. It's hard to see those things, so we wanted to have this maxim. Uniform priors, seemingly non-informative, is actually informative. So uniform prior, why people like uniform priors? Uniform priors facilitate some Bayesian inference to help people go beyond the MLE. Even though they have likelihood function, the most straightforward way might be maximum likelihood estimation. But instead of doing that, we can just sample the likelihood because we can assume some bounded uniform priors on the parameters. So they can easily move toward the Bayesian inference, at least if they have the likelihood function. And also, uniform priors provides a way to incorporate some scientific knowledge into the bounds, because the bounds it has some hard bounds, and you can reflect some scientific knowledge to set up some range of the reasonable region, a reasonable uniform region. But one thing that may not be well known among those people who use uniform priors is that uniform bounds, the bounds in the uniform priors are hard bounds, meaning that it excludes all the possibilities beyond those bounds. And famous statistician Dr. Lindley in 1985 warns against that practice, assigning some probability of 0 to some events, excluding those in consideration in the beginning is not desirable. This is often called the Cromes rule. I beseech you to think it possible that you may be mistaken. So it is better to give some small but positive probability those things to be considered. So not completely excluding the possibilities. So here is common example, I believe, common example in the literature. When astronomers conduct the Bayesian inference, they like displaying this corner plots of the model parameters. I mean, this is scatter plot, pairwise scatter plot, and also producing some marginal posterior distribution of parameters. This is a simulated example from the real example. I tried to mimic the real corner plots that I saw many times in the literature. So as you can see in the second parameter, this is based on the uniform between -2 and 2. And clearly some posterior mass is accumulated near the bounds, 2, near 2. And it happens many times, but if I see this corner plot, my question is the scientific result robust to this bound? If this bound is wider than 2, there definitely is some posterior mass move toward that direction, and does that change the scientific result? And typically, I couldn't find those follow-up study in many articles. So we did a search. We did this survey many times, but the recent survey about the publication in June 2024, MNRAS, show that when I searched the word Bayesian in that web page, it produced 58 articles. Among these 58 articles, 17 of them display these corner plots. So among these 17 corner plots, I found that 7 of them, like 41% of them, had these boundary issues of the uniform priors. Unfortunately, I couldn't find some sensitivity check of this boundary. sensitivity of their scientific findings. But I just wanted to emphasize that this is clearly excluding all of the reasonable possibilities beyond the upper bound of the uniform prior. So it is possible that scientific result may change if we use some wide range, allowing the posterior mass move beyond that upper bound. So definitely this is one thing I believe astronomers must keep in mind when they use uniform priors. Okay, and also uniform priors are informative in high dimensions. I think this is typically argued or emphasized by Andrew Gellman in early 2000, and even recently, he's emphasizing that uniform priors may produce some informative result in some cases, even before the data kick in. So for example, when the model parameters are constrained in an increasing order, astronomers can think of these cases where multiply broken power laws, the breaking points are definitely in the order, some restricting in the order. So in that case, if we assume some uniform priors in these breaking points, then definitely in the original scale, it will be strongly preferring some quadratic function even before we see the data, and that strongly affects the result even when the data come in. So that's one thing that Andrew Gellman emphasized. Providing some caution when using uniform priors. We should think about the impact of the uniform priors in a scientific context. What's the impact of uniform prior in the actual scientific context? And jointly improper uniform priors in high dimension, definitely that's something bad. Very informative prior, becoming very informative prior. Andrew Gellman's example was about estimating regression coefficient, and then the regression coefficient has some jointly improper uniform priors. So this is one good thing we need to keep in mind when we use uniform priors. Seemingly non-informative uniform prior becomes uniform prior implicitly, unrecognized, possibly in the literature. So we wanted to warn them. So maxim for all models are subject to interpretation, but some are less contrived. This is a image that I couldn't understand what ChatGPT was talking about. So this is
subject to interpretation, no?
Yeah. So this is some mismatch between what ChatGPT interpret this maxim and my interpretation of the maxim. We wanted to emphasize some long-term community effort to construct a time-tested model and astrophysical interpretation of the models. We gave example of Asian variability study because I believe that in 2009, Kelly et al., Brandon Kelly again from this group suggested random process. This is continuous time order regressive model with order 1. With suggesting some physical interpretation of the model parameters, because random is mathematical model. We are fitting mathematical model to astronomical data and try to derive the interpretation of mathematical parameters with some physical property like the luminosity, black hole mass, and Eddington ratio, possibly related to the short-term variability and time scale of the estimated parameters in that process. And there were many other groups of people who liked that process, and they provide more empirical evidence, analyzing more large set of Asian light curves. At the same time, there were more warnings as well. Astronomers are smart. They are not blindly using the process. They also suggest that, okay, in some cases where time scale is too small, then it is possible that the physical interpretation may not hold. And then random is too simple to apply to most of the Asian, various types of variability. So there are at the same time many warnings. So this group, again, Kelly et al., suggests even more general stochastic processes for Asian variable study, and also providing physical interpretation of this mathematical model. And so far, I haven't seen some negative aspect or warnings. Maybe the class is too general to account for various types of stochastic variability of AGN, and many other follow-up studies providing more empirical evidence and strengthening some interpretation of model parameters in some cases of these stochastic processes. So I believe that this is a sequence of all of the community work to construct some trustworthy model and how we interpret the model parameters of that model. Kind of a complicated procedure to reach out to consensus or agreement. Of course, this is ongoing work. So sometime, probably in the future, astronomers may propose some downside or limitation of the process, but definitely it is ongoing. Okay, that's one thing. Maxim 5, all statistical tests have threshold, but some are missed that. I realized that when I read some papers involving some statistical hypothesis tests, astronomers tend to just show some significance level of the data evidence. But then in many cases, they don't set up the threshold. I believe that's the reason might be because astronomer has implicit threshold, like 3 sigma level, which is corresponding to p-value, the Taiwan error rate equal to 0.0027. I believe that p-value issues, going around in biology or life science, may not appear in astronomy. It's hard to appear in astronomy because astronomers have some implicit threshold, like 3 sigma, not 2 sigma, because it's hard to manipulate the data to achieve 3 sigma, but it is reasonably feasible to manipulate the data to achieve 2 sigma level. So that might be the reason why these p-value issues may not be common in astronomy. But one aspect in hypothesis testing that we want to emphasize was the threshold issues. So when there are multiple tests, for example, in the detection of first gravitational wave paper, Abbott et al. In 2016, the first detection was actually in late 2015, but the paper was published in 2016. There, the paper introduced 2 test statistics, and their argument and the detection of the first gravitational wave is based on 2 test statistics and their significance level, like 4.6 sigma level, 5.1 sigma level evidence reported in the paper. But then, of course, implicit threshold in astronomy is 3 sigma. But my question is it okay to naively comparing 4.6 sigma over 3 sigma and 5.1 sigma over 3 sigma separately? Okay, and some people may say, okay, these statistical significance level is much higher than 3 sigma, so it's a strong result. Is it okay? I believe it will double the family-wise error rate. The probability of committing at least one type of error rate among 2 tests, among multiple tests, because when we compare the significance level in a multiple testing setting, we need to account for that, okay, we are testing 2 hypothesis tests to conduct the same hypothesis testing. So in order to achieve the 3 sigma level family-wise error rate, which is implicit typical threshold, then each significance level, like 4.6 sigma, 5.1 sigma, they must be compared to 3.2 sigma threshold, which will lead to typical 3 sigma testing level in terms of family-wise error rate. But in the paper, I couldn't find their threshold because implicitly in astronomical literature is 3 sigma. But if they leave the interpretation to the readers, probably readers must keep in mind that which threshold they should use to compare these 4.6 sigma and 5.1 sigma. It should be 3.2 sigma to achieve the typical 3 sigma level of significance level. So one thing that is not well known is using first discovery rate. The statistical editor says that in astronomical journals, the use of first discovery rate is rare. So he wanted to cover some possible issues of not using first discovery rate. So the most popular method to control the family-wise error rate in astronomy is to use Bonferroni correction. Clearly dividing the 0.0027 by the number of tests we are using. So in the detection of first gravitational wave, we need to divide 0.0027 by 2. And that should be the criteria we need to compare for each test significance level. So when p-values are sorted in increasing order, Bonferroni correction is asking us to reject the null if the individual p-value is less than that threshold, 0.0027 divided by the number of tests. That will maintain the family-wise error rate equal to 0.0027, which is typical threshold in astronomical tests. But the problem of Bonferroni correction is that it is almost impossible to reject the null if the number of tests is large, even if it is actually true positive, it should be true positive, it could be rejected just because the number of tests is large. Then in that case, I mean, this case may appear in catalog, pixel-wise hypothesis testing, whether the signal is there or not. So possibly the number of tests may be large in astronomy, some situation in astronomy. What should he do? In that case, adopting first discovery rate may be alternative, because instead of controlling family-wise error rate, first discovery rate, FDR, Benjamin Hochschild, controls the expected proportion of first discoveries out of the entire discoveries. The proportion of first positive out of all of the positives, including false positive and true positives. We hope the expected proportion is less than or equal to 0.0027, 3 sigma level test. So the procedure changes from the Bonferroni correction. So we will reject the null if this individual p-value is less than or equal to 0.0027 times j, the index. Remember, we order the p-values in the increasing order. So if we do the test more and more, definitely this threshold increases more and more, definitely. So it will end up with more rejections compared to the Bonferroni correction if the number of tests is large. What is the benefit? Definitely, we will have more rejection, meaning that we will have possibly more true positive. But at the same time, it will increase the false positives, the number of false positives. That's the cost of using FDR. It will end up with more rejections, but please keep in mind that it may also increase the number of false positives. So that's one thing that statistical editor wanted to hear from us. And the last maxim. So this is based on Young's recent work. This is also group work of this CHASC. All model checks consider variations of the data, but some variants are more relevant than others. And this figure, I'm trying to interpret this figure that ChatGPT generated. So maybe the histograms, the two-dimensional histogram, they are some replicate data, the distribution of replicated data, which may be more relevant at some point, at some space with the two-dimensional space, and the others may not. Some two-dimensional histogram on the left, maybe this one less relevant, more relevant. So we wanted to emphasize that replicating data is key to both Bayesian and frequentist. Frequentist has motivation to replicate the data because the uncertainty quantification comes from the hypothetical scenario of replicating the data given the true parameter. And Bayesian inference also has motivation to replicate the data, because in order to do some model checking or prediction, we have motivation to generate posterior predictive sample. So in that situation, what we should keep in mind. So actually what we want to say is this: always be aware of what you don't know, but don't lose track of what you do know. Because when we replicate the data, if we don't condition on as much knowledge as we already know, probably that irrelevant variation of replicated data move into the uncertainty of what we don't know, which we want to know. So it may mess up the uncertainty quantification if we do not take advantage of all of the knowledge we have. So conditioning on what we do know is important when we replicate the data. And actually, astronomers has good practice of replicating data set, conditioning on the MLE of the model parameters. Of course, our motivation is to condition on the same experimental conditions, instrumental effect, exposure time, and sample size, as many conditions as we know in the replicating the data set. For example, this is a Poisson counts example. See, the y-offs, the observed Poisson counts, maybe from some of them are coming from background and some of them are coming from source of interest. So under this equation, which is reasonable, we can assume that our replicate data are our replicate data might not be the replicate data should be at least greater than or equal to the background counts. Definitely, I think I used some mistake in the notation, but based on this equation, definitely our observation is supposed to be greater than or equal to this background counts. So in replicating observed data, we should take advantage of this lower bound so that we can so that our replicate data set are more relevant to our current knowledge. And I think Yang and our group people, some of the group people also studies the impact of conditioning on the MLE or some more information in the goodness of fit test, and it turns out that it improves the power of dramatically. So this is a simple example of conditioning on MLE in goodness of fit test. And as you can see, this dashed curve is the power under when we generate the replicate data conditioning the MLE, and the solid curve is based on the goodness of test where we don't condition on the MLE when we replicate the data set. Clearly, the power is uniformly larger than the unconditional case, and we took a look at the improvement, percentage improvement. And if it were like 3 sigma significance level, typical in astronomy, conditioning actually improved the power by more than 30%, which is not small thing because it means that the same power could be achieved with 30% smaller data set. So we can save some time of the data if we use the idea of conditioning, because collecting data is money, right? Cost and time of the human being, astronomers. So those are the 6 maxims, and this is Shaoli suggests that, okay, we hope that these 6 maxims could be routinely used in astronomical data analysis, like the 6 sigma principle. Routine adoption of 6 sigma rules has improved some industrial like quality control and business, because 6 sigma is essentially having 3.4 defects in 1 million trials. The goal is having that low defect rate in engineering and quality control in engineering or industrial production. So that's our hope. We hope that astronomers keep in mind the Six Sigma, not Six, Six Maxims, as a routine in their astronomical data analysis, and we hope that it improves the scientific result in the astronomical literature. And that was kind of our homework, our report to the AAS. Finally, we did the homework after more than 5 years, but we are happy about that, I believe. That's it for today. I hope we can hear more about your opinions about these, because there is no single right answer to this question. There may be, I mean, the solution may improve over time, but we are at this current moment. Probably we couldn't go over the entire solutions in the past and possible solution in the future. So these guidelines that the AAS wanted us to prepare should improve, I believe, in the future. Must be updated. And that's it for
Thank you.
today.
Thank you.
Thank you, Tuck. Perfect timing. Any
Sorry
questions?
for not allowing the time for questions, but I will be here
Any
for
questions? Yeah, we have a question here. Tuck, go ahead.
sure.
Yeah, I don't know what maxim is this, but probably the fourth maxim. You were talking about or maybe the third. You were talking about the central limit theorem.
Oh, yeah.
And you said in one part, yeah, large data size.
Mhm.
Maybe this is a naive question. What is a large data size? Or how can we know how large is enough?
I think that's a really difficult question I have ever had.
Right, yeah.
and probably there isn't any consensus about what is large and in large data set, asymptotics. Is it enough to use the asymptotic result or not? Definitely, it depends on each researcher's confidence about the data size. If I believe, okay, my data size is large, if maybe 1 million is enough to use asymptotics, then definitely that's what that person should go in the research, and people will consider that assumption as reasonable or not. But some researcher may not be confident of the size, data size. So they may look for some finite data size solution based on finite data, and that's what Yang suggested in the recent work. Does anyone have opinion about what is large and how large is large?
Well, I mean, broadly speaking, it's a very tough question, right? Because it depends on the context, right? And in fact, a lot of work, I've done some of work recently as well, is showing that it's not really the size matters, it's really the quality matters. You can have a very large data set, but if you have the wrong quality, I mean, it's just terrible. If you look at classical statistics book, you will see people suggesting like anything n bigger than 30 is fine, right? Because the reason they do that is because bigger than 30, if you did the perfect, they're thinking about the T approximation, the normal talking to the 30-degree freedom, the normal kicks in, the difference is small, right? That's based on one aspect of the classical procedure, when you do some normal approximation. Right? But I think, so the older way of thinking about large data size is usually very limited. It's not a very useful here. What I would say is the way, for example, why do we use these large sample approximation? Often because the Gaussian approximation works well, pneumatic works well, right? But you could have checked that. For example, just run a bootstrap sample, right? Do some bootstrap to see if the normality actually reasonably hold. That's not foolproof. But if your bootstrap showing something really weird, well, you're probably just sizing too small, right? And none of those things are really, so nobody knows how to do this very rigorously. That's not a practical experience, but I think there are these tools and, validations, checking. So these things we put together is really, as you know, these things are kind of a high level, it's a guidelines, kind of vague, qualitative, but that's the nature of the beast.
Right.
We just want to make people more aware. The data science has created this false precision. It's data science, it's all this. Oh, there's so much judgment, right? So many, things we just keep trying.
Definitely, and I think
Yeah.
I really like the assumption. I mean, I like that this is an example of some assumptions can be harmful.
Yeah.
Central limit theory, because I'm thinking particularly in problems of clustering or things where we naturally assume that things can be Gaussian. And we can think that the central limit theorem provides a good base for us for assuming that, right?
Right.
Like for assuming that things can be Gaussian, and if we
Yeah.
have enough data points, they might be Gaussian.
Yeah.
Right? So I just find that assumption interesting to discuss.
That assumption has been, obviously, the whole central limit theorem has carried the statistics for a long way.
Right.
Like the entire enterprise initially probably get people excited because of stuff, and it does work in lots of time, but also as the problem gets really higher dimensional these days. You know, I mean, it's probably still. The thing that makes every thing popular like machine learning now is you don't have to think hard, you can be lazy. Like, you know, just run a thing, right?
Right.
But I think it's just equally harmful, whether it is theoretical assumption or the, you know, automated machines, you know, it's basically saying that human judgment is still needed. And lots of experience is really, you know, really important. There are some hard guidelines, for example, in these high dimensional problems, you certainly want to have more data than the number of parameters, right? These are hard guidelines, and you know it's getting close, it's not enough. You shouldn't use these things, right? And also, the other thing is that in high dimension, essentially data very sparse. In high dimension is just all over the place.
Right.
So the whole notion that, because the Gaussian data still give you a sense of there's some centrality, right? There is a, you know, a contour plot goes out, nice contours, or forget it. High dimension, just forget it, right?
Right.
Because you rarely see anyone, right? Probably astronomer knows, right? When you're out space, you can see where the neighbors are, right?
Right.
But still, I think, you know, sometimes when you don't have other way to doing it, you can still use these approximation. In fact, the tricky part is often these approximation still works, but you know how to transform problems. You know, because a problem could be very skewed, station would tell you, take a log, right? Take a log, become normal, and my ex-colleague, Chicago would tell me, if log is not enough, take another log. You know, because at some point, as we know, all data can be transformed to, because lots of those things are, you know, based on lots of experience.
Well, thanks for the nice talk.
Yeah, thanks, Carl. A lot of work, yeah.
Thank you. By the way, this is not my work. This is group's work. I'm not as I say, I'm not sure whether I
Well, without
get the
you,
credit.
you were the one who kept pushing it, because.
So the paper is an Astro PH now, right?
Could you?
The paper is now on archives on the
Yeah.
web.
Yeah, it is on our archive. Yes.
Yeah, perfect.
Any other questions? So thank you all. And the next week, is it next week, right?
No, I don't know, but because
I
we
think
have
it's on
to-
12.
So we have, in 2 weeks, I just look at the schedule, we have, Yankee Song.
Oh, Yankees is 2 weeks.
2
Okay,
weeks
okay,
from today.
okay.
And, we don't have,
Okay, we don't have, that's fine. Yeah, Yankees were great. This is a real machine learning.
Yeah,
Oh,
Kind
yeah.
of
yeah, so.
Work with Ashley, right? I mean,
Yeah, with
Yeah.
action, so that's
Yeah.
the talk to presents, where we are, is what's on processes for unsupervised, X-ray sources learning.
Any question from online? There's a chat there. I don't
I
know.
think these are old,
okay.
old questions.
Talk, are you still there?
Yeah, I'm here. Any
Okay.
other questions?
Any questions